Infinite limits and vertical asymptotes. Infinite limit. We say f of x has an infinite limit at x equals c if f of x increases without bound as x approaches c. And we write in limit notation the limit as x approaches c of f of x equals infinity. So if we look at our graph here, as x approaches c from both sides of c, remember, limits consider y values. So from the left side of c, my y values are heading up towards positive infinity. From the right side of c, again, my y values are heading up towards positive infinity. So here we would write that the limit as x approaches c of f of x equals positive infinity. Similarly, if f of x tends to negative infinity, then we would write the limit notation equals negative infinity. However, these limits do not exist because plus or minus infinity is not a real number. So here, even though we wrote that the limit equals infinity, it is implied that the limit does not exist. However, we wrote infinity because that tells us more about the behavior of the graph. Near c, from both sides of c, my y values are increasing without bound. In this example, we want to numerically evaluate each of the following limits. So here we have the limit as x approaches 5 from the left of 4x over 5 minus x. So here, if I think about directly substituting 5 into my function, I would end up with 4 times 5 is 20 over 5 minus 5, that's 0. So I would end up with 20 over 0. So that's clearly undefined. And if we think about what's happening graphically, if I have a value that makes the denominator of a rational expression 0, that value is a vertical asymptote location. So here we do know we have a vertical asymptote going on, so we have to figure out, well, what is the behavior of the graph near that asymptote on the left side of it? So x approaches 5 from the left. So if we want to approach this numerically, we would think about, well, what happens when I substitute in a value to the left of 5 that's pretty close to 5? So let's say x equals 4.9. So if I substitute in 4.9, I'm going to end up with 4 times 4.9 divided by 5 minus 4.9. So here, 4 times 4.9 gives us 19.6, and the denominator is going to be 0.1, 1/10. So overall, this is going to be 196. Now, if we think about substituting another value that's even closer to 5 on the left side of 5, so let's say x equals 4.99, that's even closer. We have 4 times 4.99 over 5 minus 4.99. That's going to give us 19.96 over 0.01 this time. So I'm thinking about taking a smaller number, 0.01, 100th. How many times does 100th go into 19.96? So that's going to happen 1,996 times. So we made the denominator smaller, and the top is pretty close to the same value, so 19.6, 19.96, but here we went from taking 1/10 and thinking about how many times that goes into 19.6 versus taking 100th and how many times that goes into 19.96. So a much bigger number. So the closer we get to 5, if we would plug in 4.999, it's going to make the denominator 1,000th. That's going to go in way more times. So these values here, 196, 1,996, they're going to get bigger and bigger. They're going to head towards positive infinity. So we wouldn't leave our answer as 20 over 0. Our answer would be positive infinity. Our answer would be positive infinity. Before we move on, we're going to answer these questions. What do you notice about directly substituting the x value into the function? So we said we ended up with 20 over 0, which is undefined. So we ended up with an undefined quantity when we substituted directly into the function our x value. And then what do you notice about the graph at each x value of the infinite limit? So let's go ahead and try to construct the graph from the information that we just found. So we can construct part of the graph near 5. So near 5, well, we plugged in 4.9, so I'm going to be kind of drastically away from 5. So 4.9, we said we got out 196, so this pretty big number, but then getting even closer to 5, so here, this is 4.99, we ended up getting an even bigger number. That was 1,000, so clearly not to scale here, right? But I got an even bigger number, so we'll say up here is 1,996. So I was going to get, just as I got closer and closer to 5, my y values were just going to get humongous. So I'm creating a vertical asymptote. So as x approaches 5 from the left side of 5, those y values are just getting huge. They're going off towards positive infinity. So what do you notice about the graph at each x value? There is a vertical asymptote there. And once we make that connection, then numerically evaluating these limits, that work can be shortened, because the bottom line is that if I end up with undefined after direct substitution, I know there's a vertical asymptote, so it's just a matter of deciding, is it going to be positive or negative infinity? So instead of plugging in all of these numbers and calculating them exactly, what we could have done instead was a sign analysis. So we could have said, well, what happens when I plug in 4.9? Well, I'd end up with a positive number over 5 minus 4.9 is another positive number. So overall, I end up with a positive. So the answer was positive infinity. So I can only do this because I know there's a vertical asymptote there, and my only option is positive or negative infinity. Alright, so in this next example, the limit as x approaches 3 from the right of x plus 2 times x minus 5 over x times x minus 3. Well, if I apply direct substitution, I'm going to end up with 5 times negative 2 over 3 times 0, or negative 10 over 0. So we know that this is going to end up being a vertical asymptote. So from the right side of 3, we just need to decide that at that vertical asymptote, are my y values going up to positive infinity or going down to negative infinity? So we can make a little bit quicker work of this. We are still going to do a numerical analysis as we're told. So we're going to substitute in, let's say 3.1, a value on the right side of 3 but close to 3. But this time I'm just going to be concerned with the sign. So here 3.1 plus 2, that's going to give me a positive number. 3.1 minus 5, that's going to give me a negative number. Then here, x, that's just 3.1, that's positive. And then 3.1 minus 3, that too is a positive number. So overall, I'm going to have a negative over a positive, so I'm going to end up with a negative value. Well, the answer then is going to be negative infinity. So remember, we wouldn't leave negative 10 over 0, we wouldn't leave undefined. We would say that this is negative infinity. Because, we'll just do a quick sketch, we know that at 3, there's a vertical asymptote, because we got undefined, we got a non-zero number over 0 after direct substitution. So we know from the right-hand side, my option was either to go up towards positive infinity or down towards negative infinity. So it turns out it's going down towards negative infinity. And now, for this last example, we're going to go ahead and look at the limit as x approaches negative 4 of 1 minus 2x over x plus 4 squared. So applying direct substitution, I am going to end up with positive 9 over 0 squared. So I am going to end up with undefined. And now I have to just think about what happens from the right and from the left of negative 4, because this is not a one-sided limit. It's a two-sided limit. So I have to do a numerical analysis from both sides. So we'll try negative 3.9 first and see what happens. Well, here I'm going to end up with 1 minus 2 times negative 3.9 over negative 3.9 plus 4 squared. Well, the bottom is always positive because it's being squared. And the top, well, these two negatives become a positive, and I'm adding it to 1, so it's positive. So this is overall going to be a positive. But now I have to check the other side as well. So I have to check what's going on at negative 4.1. So I have 1 minus 2 times negative 4.1 over negative 4.1 plus 4 squared. But again, the bottom's always positive. The top here is going to again be positive because of the two negatives. And so this is positive as well. So since they're both positive values, they're heading towards the same infinity on both sides. So this is going to be positive infinity. So if one of these was negative and the other were positive, then I would have to write does not exist. So I had to check both sides, and they both had to yield the same sign in order to write positive infinity rather than does not exist. But all of these limits do not exist because infinity and negative infinity are not real numbers. Vertical asymptote. A line x equals a is a vertical asymptote of the graph of a function y equals f of x if any of the following infinite limits occur. So if the limit from the left of a equals positive infinity, or from the right side of a equals positive infinity, or from the left side of a equals negative infinity, or from the right side of a equals negative infinity, then we'd have a vertical asymptote at a. In this example, we're going to graphically evaluate each of the following limits. So we have the limit as x approaches 0 of 1 over x squared. So we need to know what the graph of 1 over x squared looks like. So rough sketch, 1 over x squared looks like this. So near x equals 0, both sides are headed towards positive infinity. For our next two limits, we're going to need the graph of 1 over x minus 2. So this is a shift to the right 2 units of the graph of 1 over x. So 1 over x has a vertical asymptote along the y-axis, so it's going to shift to the right 2 units. And it's going to have this general shape. So we'd have to know the graph of 1 over x and how to translate it. So this is 1 over x minus 2. And now, as x approaches 2 from the left side of 2, my y values are tending down to negative infinity. So here, this would be negative infinity. And as x approaches 2, that means from both sides. Well, from the left, I went to negative infinity, but from the right, I'm heading towards positive infinity. So since they're not the same infinity, we write does not exist. So even though the first two limits also do not exist, that's implied. Here, we actually have to write it. For the next example, we need the graph of the natural log of x. So the natural log of x passes through 1, 0. So this is the graph of the natural log of x, and there is a vertical asymptote that exists on the y-axis. So as x approaches 0 from the right, my y values are going down towards negative infinity as I approach the x value 0 from the right. So I have here negative infinity. And then this is asking us to evaluate the limit as x approaches 0 from the right, but of the absolute value of the natural log of x. So the absolute value of a function means to take any part that's below the x-axis and reflect it above the x-axis. Absolute value makes all values positive. So here, the graph of the absolute value of the natural log of x would reflect that bottom part, and the part on top would stay looking the same. So this would be the graph of the absolute value of the natural log of x. And now as I approach 0 from the right-hand side, now my values are tending towards positive infinity. So here, this would be positive infinity. In this example, we're going to find the following limits given the graph. So we have the limit as x approaches 1 from the left and 1 from the right of f of x. So let's go ahead and look at 1 from the left side of 1. What's happening to our function values is that they're going up towards positive infinity. And if I look at what's happening at 1 from the right side of 1, my y values are going down towards negative infinity. As I approach 3 from the left and 3 from the right this time, so I'm looking at just a little area around 3 from the left side of 3. So if I look at what's happening to the y values from the left side of 3, they are getting close to a specific value, that y value being 1. So the limit from the left of 3 is 1. But as I approach 3 from the right side of 3, if I look at what's happening to those y values, I'm heading up towards positive infinity. And moving down as I approach 4 from the left and 4 from the right, so again we're going to go ahead and come at each value in just a little area around that number. So from the left side of 4, I'm getting close to 4. From the left hand side, my y values are going down towards negative infinity. But from the right side of 4, so if I think about what's going on from the right hand side of 4, I'm getting closer to the y value 2. So we can see that y value lines up with positive 2. And these last two examples are a little bit different. So here we have the limit as x approaches positive infinity and the limit as x approaches negative infinity. So let's talk about what's going on there for a second. So as x values approach positive infinity is way over here, so I'm thinking about what's going on as my x values are getting bigger and bigger. So it's always about what's going on with the y values. So as x values get bigger and bigger, it looks like my y values are getting closer and closer to a specific y value, that y value being positive 3. So as x values go towards positive infinity, get really big, the y values on this example are going towards positive 3. And as x approaches negative infinity, so as I think about those values that are going all the way to the far left, what's happening to the y values? The y values are getting closer and closer to 0. They're getting closer and closer to the x-axis, which is the y value 0. And just to note, these last two examples are called limits at infinity, and we'll look at them more closely a little bit later. In this example, we are going to work backwards, and we're going to draw the graph of a function f of x with domain everything from negative infinity to 4 and 4 to infinity, so everything except for 4 is the domain. And we're going to satisfy these limit conditions. So we're going to start out with the limit as x approaches 2 from the left of f of x has to equal positive 4. So I'm going to go ahead and start by thinking about the value 2, positive 2. From the left-hand side, I'm going to have to get close to 4. So I'm going to go ahead and just start slightly to the left of the x value 2. So I don't want to start very far over. I want to say just close to the x value 2 from the left-hand side. So I have the freedom to draw whatever shape I want as long as I get close to 4 from the left-hand side. And remember that a limit to exist doesn't have to be defined. So I could end at an open circle or a closed circle, at least for right now. So I'm always going to go ahead and just assume that they're open circles, and because maybe later in the problem we might need to fill that value in somewhere, define f of x somewhere at x equals 2. So far we've satisfied the first condition. The second condition, the limit as x approaches 2 from the right of f of x has to equal f of 2. So I want to be clear what this is saying. This is saying that the limit as I come at 2 from the right hand side has to equal the function value. So it's not specifically telling me that I have to get close to the y value 2. This is saying that the limit has to actually equal the function value, or the point. So that's what f of 2 is. So I'm just going to go ahead and write that label. It's asking me to equal the function value, or that's where the point is defined. So as I come at 2 from the right hand side, again I have the freedom to this time choose whatever y value I want, but it has to be a closed circle that I end at. It has to be the function value. So as I approach 2 from the right side of 2, and I'm just going to start just a little bit over on the right hand side. So I'm going to go ahead and draw a graph that looks like this. I'm going to go ahead and approach from the right side of 2, and I have to end at f of 2, at the function value. I arbitrarily decided to make that function value -3. There was no restriction on it. So this is my second part being satisfied. From the right side of 2, my function equals f of 2, the function value. I didn't have to be -3, so all our graphs are going to look different as we construct these. The third condition, I want to make sure that the limit as x approaches 2 does not exist. So in that last part, what I could have done was ended at +4 and filled that hole, but then I wouldn't have satisfied this third condition, that the limit as x approaches 2 does not exist. So I could choose whatever value to put the filled in circle I want in part 2, but now that we know part 3 here, I couldn't have put it at the y value 4, because that would make the limit actually exist. So here, so far, so good. And then we'll go ahead and take a look at the last condition. As x approaches 4 from the right side of 4, f of x equals +infinity. So from the right hand side of 4, my y values have to go towards +infinity. Well, by definition, that makes 4 a vertical asymptote. So this condition right here means that I'm going to have a vertical asymptote at x equals 4. So I'm going to go ahead and sketch an asymptote there. And notice that it corresponds with our domain. I cannot exist at the x value 4. So from the right side of 4, I'm going to have to go towards +infinity. That's where my y values are going to have to head, towards +infinity. So now I've satisfied all 3 conditions, but I actually haven't satisfied the domain part completely. So the domain is everything. Everything on this graph has to exist except at the x value 4. And right now, I have a little bit of a gap going on. I have a few gaps. So over here on the left-hand side, I can do whatever I want. I can go ahead and just connect this side and say that it's going to go down towards -infinity. In between, right here, if I pick up where I left off, I can go ahead and say this also goes towards +infinity, but that was a choice. I could have turned it around and said it went towards -infinity. That's fine as well. There are kind of a lot of different options for these graphs once you satisfy the specific conditions. Another thing that I could have done at 4, just to show it in maybe a different color, is I could have went ahead and ended at an open circle along that vertical asymptote. Just as long as I'm not defined there, that's fine, and I only need to be approaching it from one side to be considered a vertical asymptote. And then on the other side of the graph, just to finish it out, we can go ahead and say it continues off like this. Maybe it looks like it has a horizontal asymptote, maybe at 1. But at that point, we just want to make sure we're clearly saying it is defined everywhere else. One of the other things that kind of just comes up on these graphs that I'll mention is that sometimes students draw not a function. So they draw a graph, but they don't draw a function. So we have to be careful about that. A function has to pass the vertical line test. So when you're done with your graph, when you go back and take a look at it, you want to make sure that everywhere you can draw a vertical line and only cross at one point, right? Pass the vertical line test to be a function. So we're fine everywhere. we're only crossing one time, but at one point. But sometimes students just like continue on a little too much and they start to overlap, and then you don't have a function anymore. You have a graph, but no longer a function. So I will erase these. This is an accurate graph. Let's go ahead and do another example of drawing the graph of a function. Students tend to struggle with these type. So this time the domain is everything except positive 3. We'll go ahead and start with our first condition. So the limit as x approaches -1 from the left has to equal positive 4. So let's go ahead and emphasize -1. From the left side of -1, I have to approach positive 4. So something like this. And again, keep in mind, I'm just starting just to the left of -1. I don't want to go too far over. And I'm keeping it an open circle for now. Maybe we'll have to fill it in later. We're not sure yet. The limit as x approaches -1 from the right of f of x equals 0. So now we're approaching -1, but from the right-hand side. And I have to get closer to the y value 0, which is the x-axis. So maybe it looks something like this. And again, I'm going to end at an open circle for now. Again, maybe later we may have to fill one of those in. We're not sure yet. The third condition, the limit as x approaches 3 of f of x is equal to -infinity. So as I get close to 3, the x value 3, from both sides of 3, my graph has to go towards -infinity. So that means that we have a vertical asymptote. So I have a vertical asymptote at x equals 3. So I'm going to go ahead and sketch that vertical asymptote. So what we know is that both sides go down to -infinity. So from the left side of 3 and from the right side of 3, I go down to -infinity. And if I just peek ahead for a second, I have no requirements for anything between 3 and 5. 5 is the next x value. And I have no requirements between -1 and 3 either. So I can fill in the graph between -1 and 3 right now, however I want. So I can go ahead and just pick up where I left off over here and connect it. As long as it's defined all the way across, I can't leave a big gap because of the domain. And then I'll also be able to, beyond or between 3 and 5, do anything I want either. So when I look at this next one, the limit as x approaches 5 of f of x equals 1. So as I get close to 5, from both sides, I have to approach 1. Well, I'll just pick up where I left off here and get closer to 1. And I'm going to go ahead and do this. So I'm leaving it an open circle. So from both sides of 5, I'm approaching 1. So the limit exists. It doesn't have to be filled in. So I always just go ahead and leave them as open circles until I find out they have to be otherwise. And the fourth condition actually tells me I had to leave this open. So the limit as x approaches 5 of f of 5 does not equal f of 5. So this actually tells me I cannot have the value filled in at the limit. So at 1, I cannot have f of 5 exist there. So that means f of 5 is going to have to exist somewhere else, because the domain is everything except for 3. So 5 has to have a corresponding y value, and I can put it wherever I want. So I'm going to go ahead and throw f of 5 up here at 4. So it can be anywhere except the limit value, because we know that the limit doesn't equal the function's value. And then finally, we'll go ahead and look at the last one. This isn't a limit, this is a function value. It says that f of -1 equals -1. So this is telling me exactly where to put the filled in point. So at the x value -1, I'm going to go ahead and fill in the point down here at the y value -1. So what that means is that earlier, when we were answering or trying to satisfy the first two parts, I couldn't have made them filled in circles, because then I wouldn't have a function anymore. So let's just say earlier I decided to make one side filled in and the other side not filled in. I would have to go back and erase that, because I'm told exactly where to put the function value, and it can't go in more than one place. So now I'm just going to finish off the left-hand side. Right, we have no conditions over here. It can do whatever it wants, so I'm just going to decide it's going to go down towards negative infinity over here. One of the most popular indeterminate forms is 0 over 0, but let's talk a bit more about indeterminate forms. We'll start by letting a be a positive real number. So then let's consider the quantity infinity times this positive real number. Well, the infinity is going to take over this product, so the answer is just going to be positive infinity. And if I have infinity times a negative number, real number, then it's going to be negative infinity. So we're going to keep the negative, but the infinity part is still going to take over. If I have infinity times infinity, well, that's still going to be infinity. And if I have infinity times negative infinity, a positive times a negative in this case is still going to be a negative. So we have negative infinity. So all of these quantities sort of make sense. We can reason them out. Here we have infinity plus infinity. Well, yeah, so infinity plus infinity, reasonable to say that's still infinity. And this last one's kind of interesting. So negative infinity minus infinity. Well, what we know about subtraction is that we would think about it as adding the opposite. So if I have negative infinity plus more negative infinity, that's still going to be negative infinity. So all of these quantities that are on the left can be determined. They make sense. But now over here off to the right, let's look at some indeterminate forms, right? Quantities that cannot be determined, that don't quite make sense. So the idea of infinity times 0. So in this case, which one wins? So infinity, right? Infinity times anything is infinity. Well, no, that doesn't make sense because 0 times anything is 0. So here, infinity times 0 cannot be determined. Infinity minus infinity. So is that 0? Same thing minus the same thing is 0? Or, is the infinity on the left bigger than the infinity on the right? So the answer is infinity. So this also cannot be determined. And again, we've already talked about the idea of 0 divided by 0 being an indeterminate quantity. There are actually a few more indeterminate quantities that involve powers. So 1 to the infinity, 0 to the 0, infinity to the 0. But those aren't quantities that we can quite deal with yet, and there is a special rule that we're going to go ahead and look at a bit later that handles those other indeterminate forms. Now let's take a look at some examples. We're asked to find the limit as x approaches 0 from the left of the quantity cosecant x minus 1 over x squared. So here off to the right, I have the graphs of cosecant x and 1 over x squared sketched. These are graphs that we should be familiar with as basic functions. And what we want to do is think about each one individually and what's happening on each graph as x values are getting closer to 0 from the left-hand side. So on the cosecant x graph, on the left side of 0, the y values are going down to negative infinity. So on the left side of 0, we're going down to negative infinity. And then minus what's happening on the graph of 1 over x squared as I approach the x value 0 from the left. So from the left, the y values are going up to positive infinity. So I now have a positive infinity here. And so the question is, can this quantity be determined? Negative infinity minus infinity. Well, I can turn this into adding the opposite. So I have negative infinity plus negative infinity, which is negative infinity overall. So even though I didn't know what the overall function looked like, cosecant x minus 1 over x squared, I do know what each individual function looks like. I can sketch its graph and then analyze each piece, and that difference could be determined. And now in this example, we're asked to find the limit as x approaches pi over 2 from the left of x times tangent x. So on this one here, we don't know what the graph of x times tangent x looks like. So we want to think about each function individually. And when I think about the function just x, if I think about just going ahead and plugging in pi over 2 into x, I'm just going to get out pi over 2. So this first part of the product I can determine by just doing direct substitution into that part. So if I plug in pi over 2 into x, I just get out pi over 2. The issue comes when I think about plugging pi over 2 into the tangent x function. So I've gone ahead and sketched tangent x, and if I think about pi over 2, there's a vertical asymptote there. But we're looking at pi over 2 from the left. So on the left side of pi over 2, as I approach the asymptote, I'm going up towards positive infinity. So here, this is going to be pi over 2 times positive infinity. So I have a positive real number times infinity. Well, that infinity is just going to take over, so the overall answer here is infinity. So this is not the graph of x times tangent x, it's just the graph of tangent x, but we could analyze this product. So this first part would be just a number, and we can think about the graph of y over x if we y equals x if we really want to, although we can just do direct substitution on that, it's not a problem. But y equals x is just a line with slope 1 passing through the origin. So when you plug in pi over 2 into y equals x, you get out pi over 2, right? It's the identity function. Whatever you plug in, you get out. So, you know, x approaches pi over 2 from the left. Well, from both sides, when you plug in pi over 2, you get out pi over 2. So it just wasn't necessary to sketch the graph. The interesting one is tangent, because at pi over 2 there was a vertical asymptote, so we had to determine whether it was positive or negative infinity.